Alright, so in this part I'm going to talk about some further discussions of missing data analysis, and I will talk about some of the reporting guidelines of what are the things that we should report when we write about our missing data analysis. And for this I'm just going to use the reporting the use of multiple imputation for missing data in higher education research as the reference. And in this particular discussion lecture, I'm going to talk a bit more about assumptions, why multiple imputation is better than other type of imputations, what are the process of multiple imputation. Is there just one process, or there are multiple ways of doing multiple imputation, and how does the multiple imputation process that I have discussed in the main lecture work, and how to get an estimate from the multiple imputation. And then I will talk a bit about how to report your analysis and what to do in complex scenarios in the part 7. So in terms of the assumption, here are the very brief rediscussion of the assumption. The first assumption is the missing completely at random, and in here you have to justify that whatever data was missing for no reason, for random reasons. There are no observed or unobserved reasons that can explain your data's missingness. Missing at random is something where your data is missing, and that can be explained by some of the measurements that you have in your data set. And if you have those observations in your data set, then we can try to control for the association between those observed and the missing variable values, to try to reduce the amount of bias under the MAR assumption. Basically what that means is that we can try to use the imputation model to impute the reasonable missing values based on the observed values that we already have of the other variables that are highly associated with the missing variable. And last one is that MNAR is basically where you have some missing values, but you cannot really explain based on the data that you have in your hand why those are missing. And even if you build a imputation model, that cannot really address the missing data problem in a reasonable way, and the bias still persists even if you have your imputation model that are built with many covariates. Alright, just a recap of the multiple imputation process is that it is often claimed that multiple imputation method is superior than the ad hoc methods, then the complete case analysis. Even if when you have less than 5% of the data missing, you can still use multiple imputation in a reasonable way, and that would be actually useful to build a very reasonable imputation model if you have some some variables that are highly associated with the missing variable values. And also, even if you are getting some new data based on this multiple imputation in the data set where you still have very small amount of missing values, but it is still giving you more power. So more data is always better, right? And multiple imputation is better than single imputation because in a single imputation, when we are imputing a data, we are just saying that age is 34 for this person. Even though we have not observed this, we are basically putting an estimate over there based on our reasonable guess, but still that is an estimate. When we are saying that age is 34, that might not be 34 exactly. It could be 35, it could be 40, or it could be even 25, right? We don't know. So when we are using single imputation, we are treating that missing variable value as if it was observed. There is no difference between another person's age whose age was exactly observed, it was not missing, and it was 40. There is no uncertainty about it, right? But when we are imputing a value, we cannot simply ignore that uncertainty, and that's where the multiple imputation excels. And this multiple imputation works under the MAR assumption, but even if you have MCAR assumption, you can still impute. It should not differ too much. But if you have MNAR or NMAR, in that case what will happen is that you can impute based on the imputation model that you have built, but you might not be able to get rid of all of the problems or bias issues because your imputation model is basically not adequate to impute a reasonable number. And basically how it works is that it uses the correlated nature of your data. Say for example, one person whose age is 40, his income is, say for example, 100,000, and then he lives in a good neighborhood, say for example, everything is interconnected. So when you are looking at a person's data, everything is interconnected. So under the MAR assumption, what we are really trying to do based on the imputation model is basically leveraging this correlated nature of the data to improve our imputation. And one of the key feature of this multiple imputation is that it's not about just imputing one value, coming up with the best value. That is not the objective here. The objective here is to build a distribution of the variable, and based on that distribution we are just sampling some reasonable values. And this is a bit important to understand, that predicting a reasonable value is a good thing, that's for sure, but that is not our ultimate goal. Our ultimate goal is to get rid of the bias that the missingness creates in our analysis. Alright, so what are the different types of multiple imputation we can do? The most popular one is known as the multiple imputation by chained equation, or MICE, and there are many different versions of this MICE, and in R and in Stata, in SAS, I think everywhere this MICE version is implemented. There is another version of multivariate normal imputation, and it is only for continuous variables, and it uses the data augmentation to do the multiple imputation, but the joint multivariate normality assumption might not be suitable or realistic for many scenarios. That's where this MICE is a very robust algorithm where it can deal with any type of variables, continuous, categorical, binary. So this multiple imputation is gaining more and more popularity. So how does this MICE really work? So remember in the main discussion I was talking about a couple of steps. All of these steps are applicable to this MICE. So the way this MICE works is that initially it provides starting values for all missing data. Then we select a value of M, how many imputations of data set we want to build, say M equal to 5, say for example. And then we select the imputation model, and we select the imputation model based on the variables that are missing, and it is not essential that all of the variables in the dataset should to use in all of the imputation models. Say for example, if you have missing value of age, then if you have missing value of cholesterol, if you have missing value of BMI, you do not need to use all of the covariates to impute all of these three variables that has missing values. You can customize, and it is often preferred approach to think very hard about each variable separately to build those imputation models when possible. And then each variables are imputation one by one sequentially from the distribution of the variables. So this idea is very important. We are not just talking about just a predicted value. We are talking about a distribution of predicted values based on which we are simply sampling some observations to impute in our imputed data, and that gives us some realistic randomness in the process. So how do we estimate a parameter estimate from mice? We have m number of imputed data, and then we apply say for example logistic regression in all of those imputed data. If we have 5 imputed data, we will have 5 logistic regressions, and then we pool or average out the 5 different slopes, and we get the pooled estimate, and we also calculate the standard error based on Rubin's rule that captures the uncertainty in the imputation process. Alright, so what are the things we need to report when we conduct our analysis using mice? The first thing we should report is rate of missingness in the variables. If you have 5 variables that have some missingness, you need to mention what are the rates of missingness of each of these variables. Usually when you create the missing data, you perform the missing data analysis, usually people try to create a complete case and then compare it with the original number of samples they have in their dataset, and then say for example if you are losing 40% of the data because you created the complete case, that's what you should also report. You should think about reasons for why the variables have missing data. Is it because of some sort of stigma? Was that a question that was randomly refused to answer? Maybe they were feeling something by mistake, or were they fearful about government intervention, that government is collecting their information? So it is very helpful for an analyst to think about why the data could be missing, and then you have to clearly mention what is the assumption under which you are operating. Is it a MAR assumption? Is it a missing completely at random assumption, MNAR assumption? Only under the MAR assumption you can do this imputation build up and models. You have to report the M. Is 20 your M or 5 your M? The more is better based on the based on the computational resource that you have in your hand. Also you need to report the software version, because many softwares have many different defaults. You have to be very clear about the imputation models. What are the covariates that you are using? Did you include the outcome variable? Are you including any of the auxiliary variables? Are you using any of the covariates that are highly correlated? The more variable that you add, the more the MAR assumption is becoming plausible. And also you have to think about not only the variables but also the model specification, whether you are including interaction polynomial terms, or whether you are imputing binary categorical variables separately before imputing the continuous variables and things like that. Often that is helpful to have a sequential process. You have to report which pooling method you are using. Usually people use Rubin's rule, and then you have to report if you see any discrepancy of the observed value versus the imputed value. Usually people draw histogram or density plots for this. Also, it is a very good idea to report whether different imputations are, or the different imputed data sets are resulting in very different results or not. Say for example, if you have imputed 20 times, out of those 20 times, how many times the results were very different compared to the other results. And it is a very good idea to change the seed and try to see, when you change the seed or number of m and different parameters, whether you are getting the results that are not too sensitive to changing these parameters. If changing your m is changing your results, maybe it is time for you to choose a higher value of m. And also you have to report in such a way that the reader, after reading it, understands how you have done your mice analysis, and they can then reproduce the analysis if they had access to your dataset. One common question is what do you do when you have outcome that is missing? One approach that I have already discussed is the multiple imputation and then deletion. Basically you use all of the information, including the missing observation, including the rows that have missing observation, to do your mice analysis. But after the analysis, before doing your main, after the missing data analysis, before doing your main analysis or regression, then you delete your outcome information. If you are thinking of keeping those imputed outcome variables or values in your analysis, then you need to justify why do you think that is adding anything in your analysis. And obviously MID approach is not foolproof. There are some controversy in recent years. And one common question is that when you know that your imputation model is not perfect, there are some variables that are not measured in your dataset that could be helpful in building a better imputation model. What do you do? So basically we're talking about maybe an MNAR situation where you might have some variables that are unobserved. Can you still do missing data imputation? Basically the argument is that even if you are dealing with subject area knowledge and all that, and you are working with real data set, sometimes it is possible that you might not know which variables were relevant that are not measured in your data set. And also you have to think about in a pragmatic way that is it some good that you are doing when you are doing the missing data analysis by creating an imputation model based on whatever variable you have? Of course you should acknowledge that you do not have all of the variables, but is it better than the complete case analysis? That question you need to ask yourself. Before completely abandon your missing data analysis, you need to have a very good justification why you are not doing any missing data imputation. Is it because you do not have one or two variables that are not available, and you think that without those variables whatever imputation model you build is useless, or you think it might still have some impact in reducing some bias? Of course, reducing all bias might not be possible in most scenarios anyway. And how much is too much? Like say for example, when you have 20% missing, 30% missing, 40% missing? Is there a cut point beyond which you give up and say that your analysis is not worth doing? There are some research that suggested that even with more than 40% missing, the results were reasonable, but it kind of varies area to area and analysis to analysis, so there is no known cut point that I know of. What can you do when you have longitudinal data? So there is a huge amount of literature that is building up right now, and even some software packages are being prepared for this, especially under mice. Whenever you see some method that starts with 2L, those methods are usually for longitudinal scenarios, and there is this mice ads package, and there is this additional package that came out, and you might want to look for method. If you are dealing for longitudinal data, you might want to look for methods that are suitable for handling longitudinal data. This book is particularly very useful in that regard. Thank you.